Hi everyone and welcome to the learning curve. In this video we'll be looking at how to calculate the sample size. This is a common topic in the study of statistics as well as research methods for students who are conducting survey work or related field work where it is required to determine the number of participants or sample size for those studies. Here we are told in number 1 that some scientists were interested in testing some birds for avian influenza, bird flu. 150 birds were tested and 60 were found to be infected. They wanted to estimate the proportion P of the infected birds. What is the sample size required so that the maximum error of the estimate, in other words called the margin of error, is 0.04 or 4% with a 90% confidence. Now there are two types of confidence intervals that are being illustrated in this or will be illustrated in this lesson. That is confidence intervals for means and confidence intervals for proportions. There are several questions that we will be going through. This particular question is concerned with estimating the sample size or number of participants, in other words, in the study that will guarantee a maximum margin of error of 4% and a confidence level of 90%. And we are interested in estimating the proportion P of infected birds. So this is clearly a confidence interval for proportions or percentages. So we need to firstly establish what the formula is for confidence intervals for proportions. So the formula for confidence intervals for proportions is n, where n represents the sample size itself that we're trying to calculate, is equal to z squared. Z is the table reading from the standard normal table associated with the level of confidence of the estimate, multiplied by p hat, which is the sample proportion, times q hat, which is always 1 minus p hat, and we're dividing by the square of the maximum tolerable error or margin of error. This is p hat q hat. So this will be equal to, so let's state a few facts before we calculate this. It's useful to know that for a 90% confidence level, the table reading for a 90% confidence level is 1.65 roughly, or more precisely 1.645. It's also useful to know that for a 95% confidence interval, the table reading is 1.96, and that for a 99% confidence interval, the table reading is 2.57. So that's 2.576, or 2.58 would be fine. So for 90%, 1.65 would also be acceptable, and 2.58 is acceptable for 99% as well. These are the most common confidence levels that are used when determining the sample size. So you can really memorize these, even though towards the end of this lesson I will show you how to read them from the table, the standard normal table here. Okay, but it's always useful to just know these offhand so that you can easily go through your calculations. Okay, so let's go about this. So we're going to do substitution based on the information given to us in the problem. So we know that Z, based on the fact that the confidence level that is being used for this sample size calculation is 90%, is 1.645. So we just insert there 1.645 squared. Here we're going to multiply by p hat q hat, but we don't have that value calculated as yet. So I'm going to go ahead and substitute E, which is the error, and the maximum error that the researchers are willing to tolerate is 4% or 0.04. So in the denominator here, we're going to have 0.04 squared. Now let's go about working out p hat and q hat. So I'm going to do that right here. So p hat, which is the sample proportion, is simply calculated as x divided by n. That's how we calculate the sample proportion, where x is the number of successes and n is the total sample size. In this case, the total number of successes is 60. 60 birds were infected from out of a sample of 150. And so when we divide 60 here by 150, that is going to give us the value for p hat. So 60 divided by 150 is 40%, or 0.4. So we have found that p hat is 0.4. So if p hat is 0.4, therefore we can calculate q hat. Q hat is always going to be equal to 1 minus p hat. Right, so 1 minus p hat, which is 1 minus 0.4, and that's going to give us 60%, or 0.6. Okay, 60% or 0.6. So now we've found p hat and q hat, and we're going to substitute them here. So this will be 0.6 multiplied by 0.4, or we could just bracket them. And there we have our problem set up. So here I'm going to go ahead and work out the numerator fully, which is 1.645 squared, which is 2.71 roughly, then multiplied by 0.6, then multiplied by 0.4, and that will give us 0.649446. All the decimal places are used there for absolute precision. And then we're going to square the 0.04 in the denominator. All right, so we're squaring 0.04. When we square 0.04, we're going to get 0.0016. And when we divide these, whatever result we get is going to give us a sample size that is required in order to guarantee a maximum tolerable error of 4% and a confidence level of the estimate of 90%. So dividing here by 0.016 gives us roughly 406. Right, so the required sample size in this case would be approximately 406. This sample size of 406 would be required to conduct this study, guaranteeing a maximum tolerable error of 4% and a confidence level of 90%. Right? And so that is how we calculate sample size for estimates of proportions. Now let's look at this one. In this one, we are told that a department store wishes to estimate with a 95% level of confidence and a maximum error of plus or minus 3 the true mean number of customers who visit the store each month. The question is, what sample size is required to carry out this estimate, given that the standard deviation from a pilot study was 15? In the first question, we were estimating the sample size required for a study where the intention was to estimate a population proportion. In this case, the aim is to estimate the population mean. So here we are interested in calculating the sample size that is required to estimate the population mean. So the formula is different. The formula that we use to calculate the sample size for an estimate of population means is this. So it's n equal z multiplied by z, again here is the table reading that is associated with the level of confidence of the estimate, multiplied by s, where s represents the standard deviation of the sample. So s represents the standard deviation of the sample. And we have the maximum tolerable error of e. And we're going to square all of this. We're going to simplify what's inside the bracket and then square. So since we are using a 95% confidence here, this is 1.96, 1.645, and of course 2.5 right there. Okay, now since we're using a confidence level of 95% for this estimate, then we are going to use the z-value of 1.96. So this would therefore be 1.96 multiplied by the given standard deviation from the pilot study of 15. Typically the information for S, the standard deviation in this problem, where we're calculating the sample size for an estimate of mean, typically that will come from either previous literature that has been canvassed or from some pilot study that is carried out. Similarly, p-hat would normally come from a previous literature that has been canvassed or previous pilot studies that have been carried out. So that's where p-hat and S would normally come from for these calculations, either from previous literature or from a pilot study that is carried out. So here we're dividing by the maximum tolerable error, which is 3. So we don't need to put plus or minus 3, because whether you square a negative or a positive, the answer is still going to be positive. So here I insert the value 3, and now we're going to simplify this very easily. We're going to work out what's inside the bracket here first. So that is, we're going to multiply 1.96 by 15. So 1.96 multiplied by 15, and then we divide by 3, and that will give us 9.8. Right, so you multiply 1.96 by 15, click the equal sign, then divide by 3, which is the denominator value. We get 9.8, which we're going to square 9.8. And when we square 9.8, we got approximately 96. So we need 96 persons to participate in this study. This is our required sample size. So 96 persons to participate in this study in order to ensure that, right, so we need 96 persons to participate in this study in order to ensure that the maximum error or margin of error would be 3, and also to ensure that the level of confidence of 95% is satisfied. So that is how we calculate sample size, or required sample size, for surveys and other types of studies when the desire is to estimate a mean. So we've looked at how to calculate the required sample size for estimates of means, and we've looked at calculating the sample size for estimates of proportions. Now we're going to look at some other situations simulating both of these. In number 3, it says Lambert, Stein, Everidge, Forey, 2006 conducted a study in primary health care setting on cross-cultural validation of heel bone compliance to high blood pressure therapy scale in South Africa, which reveals a prevalence rate of 50%, which will be used in this study. So in a situation like this, where you have the prevalence rate being 50%, that prevalence rate would be like the value of a p-hat, right? And we're going to just add something to this. We're going to say here that the desired margin of error is 5%, and the level of confidence of the estimate is 99%. What sample size is required? What sample size is required to estimate the true population percentage. So what sample size is required to estimate the true population percentage? True population proportion or percentage. All right, so let's just add in that piece for completeness. Okay, so in order to compute the sample size here, what we need is to recognize that this is a confidence interval for proportions. So we need to calculate this is a sample size rather for proportions. So we need to calculate the required sample size that will guarantee a maximum tolerable error of 5% and a level of confidence of 99%. So we're going to use the formula that we used in number 1, which is n equals z squared multiplied by p hat q hat all divided by the error term squared, or the maximum error. Since the level of confidence that is being used here is 99%, then we must remember that the z value for 99% is 2.576, or 2.58 is fine. So we're going to put here 2.576 squared. So let's push that up a little bit. So it's 2.576 squared multiplied by p hat. Now p hat is given to us in the question as 50% as indicated, which is 0.5. So if p hat is 0.5, then q hat would also be equal to 0.5, because q hat is always 1 minus p hat, which would be 1 minus 0.5, and 1 minus 0.5 would be 0.5. So what we have here therefore is 0.5 multiplied by 0.5 here, 0.5 multiplied by 0.5, which is the sample proportion p hat multiplied by q hat, and the error, which is 5%, is 0.05. I'm going to square that as well. So I'm just going to work out the numerator, 2.576 squared. So let's go 2.576 squared. And then we multiply that by 0.5 by 0.5, which gives us 1.66 roughly. And we're going to divide that 1.66. So I'm going to just write it out here, 1.66 roughly. So I'm going to write out all the decimal points, 1.658,944. I'm going to divide all of that by the square of 0.05. When you square 0.05, you get 0.0025. And so all we're going to do now is that we're going to divide 1.658,944, which is the numerator, by 0.025. And that gives us a required sample size of roughly 664 persons. That is the number of persons who are required to be included in this study to guarantee a maximum error of 5% and a confidence of 99%. All right. Generally, what you will find is that there is a relationship between the sample size and the level of confidence. Levels of confidence that are greater, if you're using a greater level of confidence, it will normally require a larger sample size compared to a smaller level of confidence. Let's look at this one. A survey is being planned to determine the mean amount of time university students spend on Instagram. A pilot study indicated that the mean time per week is 15 hours with a standard deviation of 5 hours. It is desired to estimate the mean time. So again, this is an estimate of means. It is desired to estimate the mean time spent on Instagram with within a half an hour of the true population mean. The 90% confidence interval is used. How many university students should be sampled? So again, this is an estimate of means, as was the case for number 2. So the formula would be n equal, right? So the formula here is going to be n equal z multiplied by this s, so divided by the error, z squared multiplied by s divided by the error squared, as well as s squared. We could write it that way, or we could just write everything in bracket, just so you know that you could write it that way with every element squared. Or you could write the formula like this, where you just put everything in bracket and all square the result. Now, since we're using a confidence level of 90%, then we know that a confidence level of 90% corresponds to a 1.645 Z table reading. So it will be 1.645 here, 1.645, which we are going to multiply by the standard deviation, which is given to us as 5 hours. And the error is going to be 0.5, because we're asked to estimate the mean time within half an hour, which is 0.5 of the true population mean. We're going to simplify that, and then we're going to square all of it, and then that will give us our final answer. So we're going to multiply 1.645 by 5, divide by 0.5, which is 16.45. Then we square 16.45. And when we square 16.45 here, we get a required population of required sample size rather, of roughly 271. So we need roughly 271 persons to participate in this survey in order to generate the required estimated mean time that students spend on Instagram within a margin of error of half an hour or 0.5, and a required confidence level of 90%. And that's how we do that. And let's look at this one. A survey is being planned to determine the mean amount of time university students spend studying. A pilot study indicates that the mean time per week is 18. So notice that, as I indicated earlier, the mean and standard deviation would normally come from a previous study, a pilot study, or literature that has been canvassed. It is desired to estimate the mean time within, again, half an hour of the true population mean, and the 95% confidence is used. So this will be done very similar to number 4, so I'm going to leave this one for you to practice. This is a matter of calculating the sample size for an estimate of means using this same formula here. So I'll leave that one for you to practice. Let's look at number 6. In number 6, in a proposed study, a researcher wants to estimate the mean earnings of a large group of employees in the manufacturing sector. So here, this is an estimate of means again. She wants this estimate to be in an error of at most $15 with a 99% degree of confidence. It is known from experience that the population standard deviation is 90. Determine the required sample size. So again, we're going to use n equals z multiplied by the standard deviation s divided by the maximum tolerable error of e, and we're going to square all of that. So this is going to give us, again, because the confidence level in this estimate is 99%, then recall that when it's a 99% confidence level, then the corresponding z-score is 2.576. So I'm going to insert here 2.576. That is the table reading that corresponds to a 99% level of confidence, multiplied by the standard deviation given to us of 90, all divided by the maximum tolerable error of 15, and then we're going to simply square that result, and it will give us the required sample size to guarantee the parameters that are outlined. So again, this will be 2.576 multiplied by 90. And when we divide that by 15, we get 15.456, which we are going to then square. So it's 15.456 all squared. When we square that, we get approximately 239. So we need roughly 239 participants in this study in order to guarantee a maximum error of 15 and a degree of confidence of 99. So this was an illustration of how to calculate confidence intervals for means, rather sample size for estimates of means, as well as for estimates of proportions. So I hope you found this to be very simple, easy to follow, and instructive. And before I go, I want to show you how you would be able to use the Z table or the standard normal table to derive the Z score that is used in these formulae yourself. If, for example, you get a percentage different from any one of these, you need to know that procedure, even though these three percentages are the most common. So what you generally do when you want to find the confidence, when you want to calculate the sample size that is linked to a particular level of confidence, what you simply do is this, is that you, say for example, we are interested in 90%. Let's say the confidence level is 90%. And so I want to determine this score here, Z score, to include in the formula, to insert into the formula. It's a simple process. What you do is that you take whatever the confidence level is from 100. Right, so take whatever the confidence level is from 100. That's the first step, step one. This is now how to be able to read the Z table value for yourself if you don't want to memorize these standardized ones that I gave you to the right here, or if you get a percentage different from any of these three. So let's say the confidence level is 90%. Let's say the confidence level is 90%. Then I would take 100 minus, it's 100 as in 100% here, minus 90%. So 100% minus 90% is going to give us 10%. Now, but because the standard normal curve, which is this curve here, because the standard normal curve has two tails, and these computations are done based on a two-tail assumption, what we'll have to do here is that we'll have to divide this value here, which we call alpha, by 2. So we're going to divide. So the next thing is to divide the result by 2. So divide by 2 is step 2. Divide by 2. So dividing by 2 here would give me 10 divided by 2, which is 5%, because these are percentages. This is 5%. The final step now, after dividing by 2, is to subtract that 5% itself from 100. So when you subtract the 5% from 100, so step 3, then you get 95% or 0.95. So that's the procedure. Let me go over the procedure again. When you're trying to determine the table reading for based on a certain level of confidence, you take the confidence level given from 100, then divide it by 2, and then that result you get, you subtract it from 100 as illustrated. So we get 0.95. And so what you do now is to go into the body of the standard normal table here. Go into the body of the standard normal table and look for 0.95 or the closest value to it in the body of the table. So here we go, 0.95. Eureka, we've found it. That's the closest value. These two are the closest values to 0.95. So we could either use any one of the two or add the readings for the two and divide by 2. Any of those works. It gives you a solid estimate. So this, look at the reading now. This will be 1.6. Then we go up to 5. So you see the answer is roughly 1.65. So that is how we were able to derive this 1.645, or roughly 1.65. So that is how you can use the Z table yourself to come up with the Z score to insert into the formula for calculating the sample size on your own without having to memorize these options. I hope you found this lesson to be really useful. Stay tuned to the Learning Curve Academy for much more. Thank you. And remember to like, share, and subscribe. See you soon.